Hello guys, today we're gonna start hopefully with the first lecture of assembly language programming. We're gonna go briefly. Today is gonna be just lecture 1. I'm gonna start giving hopefully 2 lectures, a lecture every day. I already have 7 ready. By today posting this, I'll have 7 ready, but I wanna keep some in case, 2 days I can't post or something. I'll post the extra ones. So lecture 1, mainly we're gonna go over the CSC 1330. This is for my students. I don't think I'm gonna be teaching this class next semester, or I'm gonna be teaching at Texas Wesleyan next semester, but I'm gonna put this for you guys. It's really important. Check it out, and if you know the other students, can you let them know that it's posted, and so they can see it. If you have any questions, any comments, please post it. I don't know, I had the slides looking this way. The other 6 lectures is different. Please, if you are subscribed, let me know which one is better. This one, this for design, or the other designs. I don't know, I prefer the other ones. But we're gonna take the C 1330, which is assembly language programming, and here's the syllabus for it. I taught it last semester, and let's see. A prerequisite for this class is any programming language. I think is good. Java. If you know any concept in programming, it's good. We're gonna go over let's go over the objectives, because I'm gonna call Boolean algebra operation, data representation. How do we represent data? Every computer has, or computers has, we feed it data, either videos, voice, pictures, floating points, numbers, text. All that is different data, and each data is represented in a different ways. Mainly in assembly, we're just gonna cover, let's say, integers, signed, unsigned. We're gonna cover floating points. We're gonna cover the characters. Characters will cover strings also, and the negative numbers, which is signed, unsigned. Mostly those data. We're not gonna go to videos or graphics or any of those. Understand the relation between different programming languages. This is really important. We're gonna know Intel and AMD processor architecture and programming. We're gonna see what's the difference between Intel and AMD, and we're gonna take the real address mode and protected mode programming, and there's another mode. We'll cover it in the chapters. We're gonna go over assembly language directives, macros, operators. Know the difference between what's a directive, what's an instruction, what's a macro, so you can programming methodologies, showing how to use assembly language to create simple level software tools and application programs, computer hardware manipulation, interaction between assembly language programs, the operating system, and other application programs. The book is the book that required assembly language for x86 processor. This, if you're gonna go over the book, I think I went and like those slides, I made them more detailed. It's not the slides I use them in class. I think those are better. Check them out, and you can find the book online. For my students, you can find the slides for the author on the public library, and you can get them. The book is available. Where did I put the book? I think it was on desktop. 1 minute. Here's the book. This is the 6th edition. I have the 7th edition. I don't know if the 6th edition, the 7th edition is available as a PDF online. Check it. I haven't checked, but I have the book as a hard copy. This is the book. You can find it online easily, and even if you buy it, I don't know, it's cheap. 6th editions doesn't there's not that much difference with the 7th edition, not that much different. So we talked about the syllabus. The others are not important, those, but this is not a class, so mainly it's a YouTube video. So let's go and start with the so it's gonna be covering the CSC 1330 Assembly Language Programming class. Chapter 1, we're gonna cover what? First thing, we're gonna start by taking a big picture of what's programming. What's a program? All those different programming languages, Java, C, C++, Assembly, Python, Lisp. What are those? Why do we have that much programming languages? What's the differences in a big picture, not in detail? We're gonna go into detail into assembly language, and this is what I'm gonna do. We're gonna program. I'm gonna show you how to program using MASM. There's also a lower level, which is NASM. MASM and NASM. MASM MASM and NASM NASM. MASM is for Microsoft, NASM is for Unix, and I'm gonna show you both. And I'm gonna show you one for the MIPS architecture. It's called the Mars Simulator. If you Google it, you'll find it. MARS, Mars Simulator. It's a MIP architecture, so the language is gonna be a little bit different. I'm gonna tell you why the language differs, and we're gonna talk why is assembly important. Why are we learning assembly? So let's start. Introduction. All computers were what? Hardwired. What do I mean by hardwired? They used to set the computer for a specific task. It can't do anything else. There's no programming. If you want to change it, you have to go and change the wiring and switch all those, change the transistors. It was hard. Then they came out with the stored programming concept, or if you heard, the von Neumann model, where I can have stored programs. We can use memory. This helped a lot. This where computers started to do more than one task. But the problem, how did we program machines? We programmed them using the machine language. What was the machine language? 0 and 1. So what? The programs were all written in 0 and 1 machine language. Think of it. If I give you a page of a code which is all 0 and 1, and try to figure it out, look at it, it's gonna be so hard. I don't think you can do that. It might take you 6 months to break it down. If you break it down, it's for just a hollow word, let's say. So after that, what came? Machine language was not sufficient to programming. Assembly language came, which is a mnemonic language, meaning it used symbols or mnemonics. For example, and it used the symbols and mnemonics for instructions. For example, the addition, it used the add, ADD. For the multiplication, it used mul, MUL. But still, that was, let's say, assembly was the first programming language after the machine. The machine, which is 0 and 1, assembly was the first programming language. It's considered hard, though I think it's so much fun, and if you learn it, it's easy, but people consider it as a hard programming language. After that came C. After that came C++, Java, and all that, and we're going to talk about it in the big picture. Programming language. So, well, what's a programming language? When I say a programming language, what is a programming language? What's a program? A program is a set of sequential instructions. Instruction 1, instruction 2. See, do I have it here? No, a sequence of instruction. Let's say I have instruction 1, instruction 2, what are those instructions for? Instructions to the CPU, Central Processing Unit. And now, us as programmers, we're what? We're given instructions to the CPU. Now, when you're using the computer, now, as I'm giving this video, I'm not giving instructions to the CPU. The operating system is giving the instructions to the CPU. We're not programming. When you do a program, it's a set of instructions to the CPU, and I'm going to explain that in detail in a little bit, but we need to know what's a CPU, what's a control unit, which are the major components of a computer, major components of a machine. I have a CPU, Central Processing Unit, or we can think of it as the brain of the computer. That's the brain, the Central Processing Unit, and it consists from three parts: the ALU, arithmetic and logic unit, responsible for the arithmetic and logic operations, the bitwise operations. We have the control unit, and this does all the coordination between the different component of or devices, or let's say between the printer, CPU, screen, keyboard, CPU. It's the control unit. It's the manager, let's say. Then we have the clock, which synchronizes all the operations in the CPU. A clock, 0 and 1. It's used for synchronization. So first part was CPU, Central Processing Unit. The other part was memory, and then we have the input output devices, and we're going to take the memory hierarchy. This is what a computer needs: a CPU, Central Processing Unit, memory, input output devices. Keyboard is considered what? An input device. Monitor is considered an output device. Those are input output devices. This is the memory hierarchy, and guys, this is really important to understand, and I think I cover it in all my classes. We have sitting on top registers, sitting on the top of the hierarchy, registers. What are registers? Registers is a type of memory which is small and fast. Small and fast. It's near the CPU. Near the CPU. That's why it's fast. Usually it resides on the CPU. On the second level, I have what? CL1, or let's say cache level 1. Cache level 1. They introduce caches to make it faster for programs. I can have a register, and I can have what? Have you heard of RAM? Random access memory. We can have registers and RAM just without those, and the computer can run. But they introduce caches to increase performance or speed of the computer. By having different level of cache, I can have only cache level 1. For example, I can have cache level 1, cache level 2, cache level 3, and they differ in the size. Meaning, cache level 1 is smaller, that's why it's faster to search or access, let's say. And then we have cache level 2, a little bit bigger in size, making it a little slower. And this is so data going back and forth between the CPU and the hard drive can reside here. And it depends, there's lots of policies. I don't want to go, that's computer architecture. I don't want to go into the policies, like replacement policies of the block. Here we save block of data instead of taking it out. Registers, remember, small memory sizes, so we can't leave the data here. So if I need the data again, I don't want to go all the way to the hard drive or RAM to get it. That's going to be expensive. Expensive, what does it mean? Costly. It's time. And in computers we always look at two things: performance, which is, let's say, speed, and memory. How much memory does it use? Those are really important measurements, let's say. So we said we have registers which reside on the CPU. Cache L1, cache L2, cache L3 reside on the motherboard. And here I took the cache L3 out. And then we have the RAM, random access memory. This is really important. Anything that runs on the computer needs to be on RAM. Needs to go on RAM. And all of those memories, what are they? You know, the valid and non-valid memory. What does that mean? If I take it, the power off, turn off the computer, or you plug off the power supply, everything on this memory is deleted. So now we need a memory that will hold what data we have, the operating system, all those, when we take the power off or when we turn it off. That's hard drive. So all of those, the top four, if we turn it off, it's wiped. Nothing will stay on it. Hard drive, it's, let's say, those are temporary storage. This is a permanent storage, and this is where the operating system resides. And what happens when you press the power button? What happens for a computer when you turn it on? It goes to the hard drive to address, let's say, 000, address 0, whatever there, and we'll have the boot sector. Boot sector for what? For booting the operating system, which is going to be residing on the hard drive, boot it to RAM. Why? Because RAM, when it's off, nothing's on it. We can't save anything on it, so we can't put the operating system on it. So the operating system is taken to RAM. When it's on RAM, it runs and the computer's working, and then we can start to do whatever we want. Turn it off, everything is wiped on those. And we're gonna see registers speed up computers, cache is speed. Size of RAM is really important. People who like games, you know, they need a really good size of RAM. All of the graphics and all of the things, those differ. We said those for the valid and non-valid, but they also differ in price. And the price goes what? Here, cheaper, more expensive. Registers are so expensive, let's say. That's why we have a small amount of registers. Usually we'll have about we're gonna take about 16 or 18 registers. Some artists have 32, some depending on the architecture. Now some will say, why don't we have 100 registers, 200 registers? Do you want to buy a computer for $500 or do you want to buy it for $1,000? This is what the price matters here. Why the price matters. Usually companies and consumers are looking for what? Cheap prices. Oh, I'm going the other way. Here's the size. On the other hand, we have the size. Registers are the smallest, then cache L1, cache L2, and size increases. We have one more factor, which is access time. Registers to access data in a register, it's really fast. Cache 1, L1 is a little bit slower than registers. Cache L2 is slower than those two, and the slowest is the hard drive. Though this is mainly the memory hierarchy, registers are really important, and when we get to them, I'm gonna go over their importance. So let's see now. This is the big picture. This is really good now. You've heard, I bet you've heard a lot about lots of programming languages named like C, C++, Java, Python, Lisp, Haskell, Perl, C Sharp, and you're going to be really saying, which one should I learn? Which one is more important? Which one is, and all that depends. And people have different opinions. Some people might like Java, honestly, and I don't recommend teaching Java at a university. C, C++ is more important than Java. If you remember when Java came out in the middle of the 90s, at the beginning of the 2000s, most schools transferred to Java. They started teaching Java instead of C and C++. The quality of the programmers, the quality of their graduates in programming was a little bit weak. They went through that a couple of years, some of them 4 or 5 years, and then all of them started going back to C++. There's some schools that teach C and Java, so that's a plus. But this is my opinion. The best thing to learn is C, and then know the object-oriented part in C++, because this is what's different in C and C++, is the object-oriented part. And what we mean by the object-oriented part, it's the classes, and that you'll take in the advanced C++, not now. And I don't want to mix it on you now and confuse you, so let's leave it. But no, it's the object-oriented part. C and C++ differ in the object-oriented part. C++ and Java are written in C. Python even is written in C. C is one of the most powerful and really good to learn programming languages, and one of the oldest, let's say, one of the oldest programming languages. All those are considered high-level programming languages. And what do I mean by high-level programming languages? High-level are close to English, easy to understand. If you look at a code, this is a code in high-level language. See out, this is a code in high-level language. 1 minute now, go back and let me use the pen. This is a code. This is saying C out, and this is C++. When I see C out, it's C++. I'm saying print to the screen A multiplied by B plus C semicolon. Anybody can read it. It's really easy to understand if you know the syntax of C++. In C we use printf, which is a function. This is the object-oriented part. In C, printf. And by the way, I'm doing C and C++ lectures together. I have about 4 hours ready. I did it for my professor who taught. He was my professor in 2003, and he asked me to do it, and I did it for him. I'm gonna do the whole class for C and C++ together. They're gonna go together. So back to high level languages, all those high level, they're close to English, nearer to human language. This is high, nearer to human language. Now this language needs to what? This is how I write programs to instruct what? The CPU. Give instructions to the CPU. That's a program. A program is a set of instructions to the CPU. So they're close to English language. How does the CPU read it? How does the CPU, what's the language of a computer? It's 0 and 1. So what we need to do is translate those high level languages to what? To machine language, which is 0 and 1. So a machine can understand. A machine doesn't understand CR. What is CR? It understands what? Zeros and ones. So we need to translate it. Think of it if two different people from two different countries, one is speaking English and one is speaking what? Indian, and none of them knows the other language. Can they communicate with each other? No. They're gonna need a translator in between to translate. So let's say the guy who knows English is gonna feed the translator with the instruction. The translator will take the instruction, translates it, and feeds the other guy with the output. And this is what happens here. High level languages go through what's called a compiler or translator. Compiler or translator translates those high level languages, and there's lots of difference in the translation process. That's the difference, let's say, between Java and C++. Java translates it to byte codes, C++ to assembly, and then to machine code or opcode. Java does the linking in the on the RAM. C++ does the linking during compilation. Java works like an interrupter. It takes one instruction at a time, translates it, and feeds it to the RAM. C++ takes the whole code, all of the instructions, translates them, and then feeds them to, and that's called compilation, and the Java is translation. So we need a compiler translator to translate from our language, which is any of those programming languages, and that's mainly the difference. In C and C++ we can do anything except, I think, HTML or web design. Python, Java, we can do in all of those networking, all of the same stuff. So English to machine language. In between, remember we said at the beginning they came with what? Assembly language. It's an in-between language. It's a low level language, not a high level language. Low near the hardware. It's more closer to the hardware, more abstract, or no, less abstract, more detailed. That's why it's considered harder. You have to know the hardware. I think most of you programmed in C, C++. Did you know what a register is? Did you need to know what a register is? No. Here in assembly, you need to know what a register is. If you didn't know, you're not going to be able to program. You're not going to be able to program. So high level language is translated using a compiler to assembly language. From assembly language, we use an assembler, what's called an assembler. Here it maps or translates this assembly language, mnemonic language, to the machine language. And I said mapping, it's a one-to-one relation. What actually it does, and this is the assembly code for this. This is the C++, this is the assembly. Here what am I doing? I'm saying move A, which is this, to EAX. I need to move anything to a register. This is a register. Then what am I doing? Multiplying what's inside EAX, which is A with B, and it saves the result in EAX. Then I'm adding what? Whatever is in EAX, which is A multiplied by B, I'm adding C to it and saving it in EAX. Here I'm saying call write integer, meaning print the whatever is in EAX to the screen. And don't worry if this looks confusing now. You're gonna learn it. You're gonna learn all this. This code, assembly code, is translated to this, and now you might say, what's this? This is not machine language, not 0 and 1. This is hexadecimal. Remember base 16? We're gonna cover it in lecture 5. Lecture 5 we'll cover it in detail, in more detail. We're gonna cover how to convert between binary, decimal, hexadecimal, how to add hexadecimal numbers, how to subtract, and mostly hexadecimals are used in addresses. So this is translated to machine code. And here we have another process that happens, is the linking process. And what do I mean by the linking? Those are instructions now. That's why they call it this. We have what is generated is an opcode, object code, or operation code, which is the executable that's gonna run or give that instruction to the CPU. And I might have more than one object code. I might have 2, 3. Here the linking between those object codes happens on this level also. The mapping translated from assembly to machine 01, and the linking all different files, object codes. The relation between high level language and assembly language: one instruction in high level language can translate to what? One or many. We can see one or many instructions, and here is many. And so this is the relation between high level languages and assembly language. Now what's the relation between assembly language and machine language? And sorry, here I didn't put it. It's going to be 1 to 1, meaning one instruction in assembly is translated to one, is mapped, let's say mapped to one instruction in machine code. Nothing is added. I'm just taking the move, representing it in binary, the EAX representing it in binary, the A representing it in binary, or binary. What I mean by binary is the machine language. After we're done, we have the object code here, the operation code or the executable, ready to what? To run. We feed it to the CPU, central processing unit, that we took earlier. And here's what happens. This is the instruction life cycle. Remember, what's instruction? A program is a set of instructions. So what happens? The first thing, the CPU fetches the instruction from memory. Remember we said the stored program concept with the von Neumann model that was introduced, so a computer can do more than one task. This is fetch from memory. The CPU fetches the first instruction from memory, decodes this instruction to know what this instruction is. Is it an addition? Is it a move? Is it a multiplication? Fetches then the operand from memory if needed. If I needed operands, and those three first instructions we needed operands. So it fetches the operand from memory, executes the instruction. Let's say a move. Here we fetch the move, we decode it, we know it's a move now, or the CPU knows it's a move. We fetch the operand, the EAX and A, we execute the move instruction. We do the moving. We move A to the accumulator, to a register which is called accumulator. We'll take it in chapter 2 in detail. Then we write back, we store it. This is what this is, the move instruction. I'm saying E A X equals A. This is the writing. This is really horrible in this. And this is what is here. If I said add, the add is, I'm saying E A X equals what? This is the register equals add whatever in EAX to what? To C plus C, and what? Save the result in EAX. So here I'm getting the add instruction, decoding it, fetching those two operands, executing the addition, getting the result of those, and I'm writing and saving the result in EAX. This is mainly the big picture. I did it briefly, but let's go and see now. Try to run it and see what happens exactly in a real scenario. And this is the compilation or the compiler. We have four stages, let's say, or four main levels. We have the pre-processing. The first step is the pre-processing, and we can implement this using, let me open the code for this, and I'm gonna run it on my Ubuntu machine. So here I already have, look here, I'll have one file, program1.cpp, and this is what the file contains. It's a C++ program. All it does is what? Print first name, last name. Oh, my first name, last name, just those. Print this as is, each on a separate line. So it's gonna just print those 3 lines. Now I need to know what's the pre-processing. Here we said pre-processing, and we can do the pre-processing by doing G++, calling the G++ compiler, and -E. This is an option, this is a command, this is an option, and this is the program I need to compile. Let's see, or do the pre-processing on, and let's do this. G++ dash capital E, be careful, it has to be capital E. And what do I have? Program .cpp. I can do this, see, but so I don't have to go and scroll back and go all over and check it. I'm gonna write all this result to a file, and I can do this by what? Using this and using the greater than sign. This is the file streaming or redirecting in Unix, Linux. Ubuntu is Unix, Linux based. I can say gate .txt or gate.preprocessing. Preprocessing. So all what was printed earlier when I ran the command is now saved in what? I can open, say gedit. Now I'm gonna open the gate.preprocessing and see what's in that file. And I'll go here, and here's the, what do you think happened? Look how much code it added to what? To my 3 lines of code. This is my code. This is my actual code that I wrote. Well, I got actually from here. This is only my code. How many lines did it add? It added 17,554 lines. Where did all that code come from? Where did all that code come from? It came from this command. But how did it come from this command? From the pre-processing. This is what the pre-processing does. You see the libraries here, they include IOStream. What are those libraries? The input output stream library. This is to use what? Cout and cin and endline. And this is not gonna work here. If but I didn't save it, that's good. Save it now, it's to use those. cout, and the end line. It's to use the input stream and output stream. It's same as the std, standard input output library in C. Those are programs or codes are already written by C++ programmers, and they include them in a library so we can use them easily without the need to rewrite the whole code. Makes it easier to program. I only write cout to print, cout to print. So all that came from this. The pre-processing is including those libraries in my code. Whatever libraries I have here, I can have here also they include math, for example, library. They include string library. Let's add them and see how much code it's gonna add. Where is the S? Why is not printing? String library, IO manipulators, C limits. We can add all those libraries, but let's see. And let's add the file streaming. I want to see how many lines of code that will add. And don't worry if you don't know those libraries by now. You'll learn them. So now, did I save it? No. Okay, include math. So it needs the C math or well, math.h. Sometimes the libraries you find with that says C something, you can write them as something.h. So this works. So now let's go and open the file and see gedit. Oh, did I close it here, the gedit file? Reload. How many lines of code? 21,934. Think of that's how many lines of code. There we have some spaces, but I think that's really huge. This is the pre-processing part. It's adding what? Those libraries code with our program. Then what do we have? We said the compilation is for process. After we do the pre-processing, we go to the compilation. The compilation is mainly checking the grammar, the syntax. What's a programming language? It's a set of vocab, like the English language or any other language, with grammar, with the syntax that is used to program. So we need to check, is the syntax of this of the program, is it right? No errors, nothing. So we do what? G++ command the compiler -o and the name of the program. And let's see here, did we generate any other codes? Okay, 1 minute. Let's do clear. Remember, we had one file. We had only this one, and I redirected this, and this is just showing that the program is open in gedit, so don't worry about that. So now I do go to the compilation, which is -big O and program.cpp. No errors, nothing. Let's see, did it add any codes? This is just the .out saying we can do what? Will it work? The program is running. This is what the program is doing. Now we have more stuff. We still have two things. We did the pre-processing, compilation. I know this might seem confusing. This is compilation, but think of this syntax, checking the errors, checking the program is running good, no errors. And here we have the assembling, converting our code to assembly code. Remember the big picture in between, from high level language to assembly code. And let's see, what was the command dash s, was it dash s capital? Okay, so let's go here, g plus plus command compiler dash s capital, and which program I want to translate, the program.cpp. Let's see, ls, we're gonna see this file created, .s meaning .assembly. I can open that file using gedit program.s, and we can go here and see this is the assembly code that was generated from our code. It's not gonna, don't think it's gonna be as big as the, it's 93 lines of code. And this is where the program starts. Usually main, this is setting up the, let's say the stack, it's use stack. EDI is another register, ESI another, source index, source destination, those are variables, move command, call. So by the end of this class, this is jump not equal, compare. Those are the commands, those are mnemonics that we use. This is what you're gonna learn by the end of this class. I think we're gonna have about, hopefully this is a long lecture, but the rest are gonna be about 30 minutes, 20 to 30 minutes lectures. We're gonna have about 45, is it 45? Yeah, 45 lectures. 45 lectures with a programming part. And I'm gonna cover the basics, everything. Then we're gonna go to the programming part. So now we still have, we converted to assembly. What do we need now? We still have one more step. What is it? The linking. Remember, pre-processing, the libraries, compiling, checking the syntax, the grammar, the vocab of the program is doing good. Then we translate it to assembly. After assembly, we do the linking, which is the we do g++ dash c small, I think c small. Let's try it. And program cpp. Let's see, did it create any files, any extra files? Do you see any extra files? Do you see it? Object opcode file. This is the file that's gonna, let's try to see it. Let's open. Here's the file. This is just saying, this is my computer, this is what we had in the cout double quotes, print as is, so it doesn't translate it. That's why I always say as is, print as is. Anything we put in double quotes, this is the other code. Look at it, it's all, you can go online, take this code, this is an object code, it's hard to translate. Take this code, and there's a lecture that I explain in if you go to the assembly language programming lecture, there's one lecture, really big lecture, explains all this in detail. What I said in detail, it's a really long lecture, I think an hour and 50 minutes. We can go and convert this code to, let's say, octal or hexadecimal, which is ABC, readable, more readable. And remember this is where the reverse engineering happens. You take this object code, this executable code, translate it to what? Hexadecimal code, object, and from that hexadecimal, if you know assembly, you can reverse engineer this code. You can get the code of, and one of the reasons you study assembly is because the reverse engineering. Why is assembly important? You can do lots of reverse engineering using assembly. You can't using C++. Knowing C++, you can't do any reverse engineering. Don't think it's that easy. You won't even understand what's there. You're gonna see it like this, same as this, even if you translate it to hexadecimal. So now we covered this. Let's go back to the slides and try to finish them. So those are the 4 steps. Remember, try to understand them: preprocessing, compilation, assembling, and linking. Here, what is assembly language? Now we need to know. Linear sequence of instructions. It's a programming language that I can write programs in. Linear sequence of instructions. Use symbols, moves, sub, add, mnemonics. Lower level of abstraction over the hardware. Very CPU specific because it's close to the hardware. Now some of you might argue and or complain that nobody uses assembly. Up to a point it's true, but you haven't seen it yet. You haven't. What do we use assembly in? We use it in drivers. Why? Assembly is faster than C and C++. Remember the big picture? If we go back to the big picture, was the memory hierarchy. I don't know why it's doing it this way. I hate it this way. But this big picture, when you write a program in assembly, this whole process, the compilation and translation, we don't need it anymore. Assembly is faster, so we use it in drivers. And what's a driver? A driver is a program or the configuration of any external device. So the drivers of any device usually is written in assembly. Why? It's faster. Game consoles is written in assembly. There's lots of applications written in assembly. You can have an embedded code. You can write your C++ code, and whenever you need to, let's say, make a part of that code faster, you can plug in some assembly code in it. So this is what's assembly language, a lower level language. Why learn assembly? Some errors. Sometimes you might have difficulties trying to debug an error in C or C++ or Java or whatever high level language you're using. In assembly, it's easier to know and fix that error. Believe me, this second point is really better understand of high level languages. Learning assembly changed the whole way I look on C and C++. And it made it really easy. It made C and C++ so easy to program. And you're gonna see. You'll judge this by the end of this class. Lower level uses, okay, reverse engineering. Remember I showed you that code, the .o code, the object or operation code. It's all zeros and ones, the executable. You can't get the code from it, but if you know assembly, you can reverse engineer it by taking this code, converting it to hexadecimal. Hexadecimal you can read. It needs some, I know you need some work to do, but still you can easily reverse engineer and get the code. So what's that? Copyright. And this is really, reverse engineering is really important, and assembly is faster. Those are why we should learn assembly. Please guys, if you like this lecture, like it, tell the other guys, especially my students. Please, if you know any other guy, tell them. Those lectures are gonna be smaller. We're gonna learn 3 assembly languages: MASM, NASM, and why is it 3 programming languages? Isn't assembly language 1? No, we have different dialogues for assembly language, different programming languages. Each machine, each architecture has its own language. The Intel have their own assembly language. The AMD own assembly language. MIPS, x86, each family, let's say, have their own assembly language. There's lots of assembly languages. When you start programming, you're gonna go online. You'll be programming in MASM. You go check online, Google some codes. You're gonna look at it. You're not gonna understand it. It's gonna be a different assembly language. So don't worry about that. I'm gonna teach you 3, so that would be good. Thank you, and I will post the second lecture in maybe 20-30 minutes. I'll leave the other lectures for the next day. I'll be posting hopefully every day. We'll hopefully finish it in, let's say, 15-20 days. We'll finish assembly. Please guys, it's really important. Really, if you want to major in computer science, if you want to be a good programmer, please do this. Do it. Lots of people learn assembly theoretical, and I'm gonna show you the theoretical part. How are you gonna know programming theoretical? No way. You're gonna forget all this. But when you program it, it's gonna stick in your mind. Thank you, and see you in the next lecture.